All right, I've already covered this at great length in the extremely long videos about disk, washer, and shell method. But if you haven't watched those and you just want a little bit of a brush up before the test, here's the deal with when to use washer and when to use disk and when to use shell. Really, I shouldn't have said disk. This is really washer because let's face it, you never get to use disk. Everything always has a hole in it pretty much, right? So the basic strategy is use the one you're more comfortable with, but also sometimes they're going to set up a question to where it only works with shell method. They might set up one that only works with washer method, but students don't tend to notice that because most students want to use washer method all the time. Students usually hate shell method, but teachers can be really conniving and figure out questions that are really only doable with shell or really hard to do with washer. So let's take a crack. All right, so let's look at this region. We've got our usual upside down parabola thing, and f of x equals 0, so it's just everything between the x-axis and this. And we're revolving around the x-axis. All right, so let's try and set it up with each of the two methods and see what happens. So shell method, we're going to do 2 pi times the integral from a to b of f minus g times x dx. Oops, this is dy problem actually. Glad we had this talk, because for the shell method, I'm going to have horizontal representative rectangles, because in the shell method they're parallel to the spin axis. So here's where this one gets rough. I got 2 pi. Now in the y direction, my integral is from 0 to 4. That's just the range of my function, my region here. But then what's f? So I need the function that defines this end of the little rectangle versus this one, right? So this end, it's not 4 minus x squared. I've actually got to put it in terms of y, because I'm doing dy for this. So I've got to rearrange my function to be a function of y. So y equals 4 minus x squared. I got to solve for x. So I'll get x squared equals 4 minus y, square root both sides, and we get x equals plus or minus the square root of 4 minus y. And what's crazy is that this side is the positive 4 minus y, and this left-hand side of the parabola is the negative 4 minus y. So right away, something's a little screwy, and that'll mess up a lot of people. Turns out washer method will be pretty straightforward. I'm kind of showing you the wrong way around why shell will not work. So f minus g is going to be square root of 4 minus y minus, because that's my right-hand function, minus my left-hand one, which is negative square root of 4 minus y. So the negatives cancel. And then I've got y dy. All right, so what's the problem here? Not only was that weird that I have two square roots, 1 plus, 1 minus, but I've actually got a serious integration problem now. Problem meaning I can't do it. Because here's what's going on. If I just wanted to integrate the square root of 4 minus y, I could do that, because my u would be 4 minus y, and therefore my du would be negative dy, and I can just stick a negative in, no big deal. But that y messes stuff up. I don't need the y to satisfy my du. So I've essentially got a product here where I can integrate either of the things on their own, but I can't integrate them together. You might be thinking, hey, we could just multiply the y in under the root and make it a y squared under the root, but then I have 4y squared minus y cubed. And now I have a serious du problem because my u would be, anyway, point is we cannot integrate this. So shell method, not bueno for this. But if you look at the washer method, all those hours ago we shot the washer video. So we got the outer radius. So in that one we just got pi times the integral of big R squared minus little r squared. And this is going to be a dx problem because for washer method we're perpendicular to the spin axis, which means our width is dx. And this is really the most important thing about washer versus shell. When they give you a spin axis, washer and shell are going to give you perpendicular rectangles. One will give you a vertical, one will give you a horizontal. And one of those is going to be better for that region, or just easier or whatever. So in this one we got pi, then x goes from negative 2 to 2. So we have slightly different, we have different limits since we're in dx instead of dy. Whereas for dy we had 0 to 4. Now we've got negative 2 to positive 2 for x. Big R is just the function 4 minus x squared. And then I square big R, so I square that, and then minus, oh look, the inner radius is just 0, because the region goes right down to the axis. So I don't even need anything right there. Oops, no minus sign, just dx. So our inner radius was just 0. So at this point, I've just got a polynomial. You might not be able to integrate this right now, but because if you did u equals 4 minus x squared, then your du is negative 2x dx, and you might be thinking, hey, wait a minute, Chris, I can't integrate that either. But yeah, you can. You just FOIL it out. Just FOIL out 4 minus x squared times 4 minus x squared. You get a polynomial. Very easy to integrate. So, turns out that washer was much better choice for all you 99% of students out there who prefer the washer method. But sometimes we'll have situations where the region is just not conducive to one or the other. So we saw this region at the end of the shell video, but since you're probably one of the people that didn't make it through the entire hour-long shell video, here it is for you fresh. So y equals x minus 1 squared is a parabola that's just sitting right there. And then x plus 1 is just a line like this. And they intersect at 3, 4, and 0, 1. All right, so there's our two graphs. So before I even draw anything in, I want to point something out here, which is that this region, no matter whether you're revolving around a vertical axis or a horizontal axis, this region really prefers vertical bars, vertical representative rectangles. And the reason for that is if I move along, if I draw, because remember we're integrating a bunch of rectangles, like infinity of them. So the integral is going to magically start at the left-hand edge here and make a little tiny itty-bitty rectangle. That'll make a longer one, then a longer one, then a longer one. And each one of these things, it's going to do its thing to, like turn it into a shell or a washer by spinning it around an axis. But the point is, as the integral moves its way along these two curves across the region, you'll notice that no matter which vertical bar I draw in, one end is always on the angled line, and the other one is always on the parabola. That's good. That means the integrals, I can use one integral to do the whole thing. But what happens if I do the same region with horizontal bars? So redraw it real quick. If I use horizontal rectangles, now I got a problem, because horizontal means my thickness is in dy, so that means the integral is going to be a dy problem, and it's going to work its way across y from one limit of integration to the other. So it's going to start at the bottom with a really short one, and then do longer ones, and oh wait, look at that. These rectangles down here have one end on the left hand of the parabola, left half of the parabola, and one on the right. So the two ends are defined by the parabola itself. But then as soon as we cross this intersection at y equals 1, now one end of the rectangles is on the line, and the other end is on the parabola. So that means I'd have to do two integrals. I'd have to do one set of integrals for this bottom portion of the region, and another set of integrals for the top half of the region. And keep in mind, we haven't even decided yet whether we're doing washer or shell. So what I'm saying is, if you look at a region like this that has a parabola in it, you pretty much want to go parallel to the center axis of the parabola. So if it's an up and down parabola, you want to use vertical bars, and if it's a horizontal parabola, like x equals y squared or something, you'd want to use horizontal bars, regardless of which method you're using. Now we'll look at the axis. Oh look, x equals -2, so that's over here. So now we just make the decision. It's already made for us. We already decided we want to do vertical bars for this region. And then they just told us the spin axis is vertical too. So what option does that leave us with? None. If this bars are parallel to the spin axis, that's a shell method. That's just the way it goes. So for this problem, if you don't do shell method, you're going to be there forever, and you'll probably still get it wrong. Because this is like not only is this not only with the washer would you have to divide it into two regions, the bottom half and the top half, but it's really hard because this parabola down here has a plus and minus square root to it. Might not even integrate. But if you're up here, actually it probably will integrate because square roots get squared away. But if you're up here, it's not a problem at all. We've just got a simple shell setup. So we'll do 2 pi. Now these are vertical bars, their width is dx. So that means we're in a dx situation, which is nice, because that means I can just take the top function just the way it is, x plus 1. Oops. And then subtract the bottom function, which is x minus 1 squared. Now, since the spin axis is to the left of the region, that's real easy. It's just x plus 2, because the spin axis coordinate is negative 2, so I did x minus negative 2 is x plus 2 dx. And now, granted, this is kind of a mess. We're going to have to FOIL this out. This x minus 1 squared, we'll have to FOIL it out. Then we'll combine terms with this thing. Then we'll FOIL all this stuff out times this stuff. But ultimately, you'll end up with a polynomial, and polynomials are really easy to integrate, so you'll plug and chug your way through it. Limits of integration I did not do, but since we're in dx, we're going from this x-coordinate, which is 0, up to this x-coordinate, which is 3. So let's integrate that, and you'll be happy. All right, last one. Another one where you'd have to split it if you do it one way, and you don't have to split it if you do it the other way. So let's see, we got two lines here. We got 1 plus x and 1 minus x. So those both have an intersect of positive 1. But then this one goes like this. This one goes like this. So this is 1 minus x, and this is 1 plus x. And y equals 0, so that's the bottom of our region. And we're revolving around negative 1. All right, so what do I prefer to do with this one? It turns out it doesn't matter much. I think you can integrate this either with shell or washer, whichever you prefer. I, of course, as I've said before, I would probably go shell, but let's take a look. If I use horizontal, so what I'm saying is, hey, let's use horizontal rectangles, because that way, as we move across the region in the y direction, one end of the rectangle is always on 1 plus x, and the other one's always on 1 minus x, so I can cover the entire region in one integral. And that's going to be a shell integral because the little rectangle is parallel to the spin axis. So if I plug and chug through the shell method, and I'll also set this one up for a washer because it's pretty straightforward. 2 pi, and then we're doing dy, it looks like. So that means I need limits of y integration, which go from 0 to 1. All right, so this, it's 1 minus x, but I need that in terms of y. So if I rearrange this, I think I'll get x equals 1 minus y. Just rearrange that equation to be a function of y. So we get 1 minus y minus the other function, 1 plus x, which y minus, so if you rearrange this function, I think you get y equals, x equals y minus 1. So y minus 1. All right, and then y plus 1, because the axis is 1 below the x-axis, so we just add 1 to it, and dy. All right, so that's an extremely straightforward integral. As you can see, there's, once you cancel out like terms here, it's going to be pretty straightforward. You might have a y squared in there or something, but that's it. So that's shell, and that's how I would probably do it. You probably prefer the washer method, despite everything I've said. So let's see how that would work. The washer method, here's what's a little bit difficult about the washer method. For washers in a horizontal spin axis, you have to do vertical rectangles. So the problem is that we have to split the region into two halves. The left half, where the rectangle is going to go from 0 to 1 plus x, and then the right half of the region, where the rectangle's top end is on 1 minus x. So this is what's painful about this one. The left region, so the left region is going to be pi times the integral from, let's see, we're doing dx, that's from negative 1 to 0, so just from here to here. And our big R is going to be 1 plus x plus 1. So this is the function 1 plus x, but then because the radius is, the axis is 1 below the x-axis, that's where this plus 1 came from. And that's all squared. Then I got to subtract the diameter of the hole, little r, which is just 1. And of course, all this is multiplied by dx. But that's just the left hand of the region. Then to that, I've got to add the integral from 0 to 1, so that's the right half of the region, of big R, which is, let's see, 1 minus x plus 1 squared. So once again, 1 minus x is just that line, but then I have to add 1 to it because I added 1 to the radius. So that's where that plus 1 is coming from. And then minus little r, which is again 1, dx. So now I've got two integrals to do. This one, this first one, is the left part of the region, and the second one is the right end of the region. So at least this one's doable both ways. It's a bit messier. You're going to have some stuff that you have to square and FOIL out, but then again, we had some squaring and FOILing to do. Actually, no, we didn't. That was a previous problem. So really, this one's way easier to do. I got confused for a second. Is that previous problem had like all kinds of nested squares and exponents and everything. But for this one, the shell method was super easy. All I'm seeing is y to the first power. Maybe I'll end up with a y squared eventually, but very straightforward. It would take me about 1 minute to finish this problem. Whereas this one, I've got two integrals to do, and they're both a lot gnarlier than the single integral I was doing in the shell method, just because there's so many squarings to do and FOILings to do and combining terms. And I got two separate integrals with two separate limits of integration, which means I can't just combine everything into one big integral. It's apples and oranges. -1 to 0 is different than 0 to 1, so I can't even combine them. So that's why you're looking at a mess, and I'd highly recommend learning the shell method. If you have even a medium hard class, I guarantee your teacher's going to put at least one question on there that can only be answered with the shell method. If you're on the AP test, they're going to have one on there where you have to know the shell method. Just the sticklers for math really emphasize the shell method. I don't know if it's because it's abstract or what, but if I was you, I'd get on board with that, unless you have a pretty easy, calculus for econ or business class, in which case you might not even know what I'm talking about, the shell method, because maybe you guys didn't even cover it. Wouldn't you be lucky?